All right, let's go over sp hybridization. We'll use the example acetylene, which is C2H2. If you're taking organic chemistry, that's the simplest alkyne, so it's also known as ethyne. If you were to draw the Lewis structure, it's going to look like this. And so let's take a look at what these bonds look like. All right, I'll do the central carbon over there on the left side. All right, so carbon, once again, has 6 electrons, so let's draw that out over here in an energy diagram for carbon. It's going to have first 2 electrons in the 1s orbital, followed by 2 more in the 2s orbital, and then the final 2 electrons are going to go into the 2p orbitals. Following Hund's rule. Okay. So when you have 2 effective pairs or 2 electron domains around the central atom, we know according to Vesper, this is going to be 180-degree bond angles. Same thing over there, 180. So what's important to remember is when you have 2 effective pairs around the central atom, um, you're going to need sp hybrid orbitals, right? So that's going to take the one. That's going to take the 1s orbitals, not the single s orbital, in this case in the second principal energy level. There's only ever one s orbital at any energy level, but take one of those and we'll take one of the p orbitals at that energy level and we're going to mix them. So, all right, so here's energy. Let me start from the bottom here. There's energy. So we're going to put this right in between the 2 here because it's going to have equal character S character and P character because we're simply mixing them in a 1-to-1 ratio. All right, so these are known as your sp orbitals. And the remaining 2p orbitals, we're just going to write them just the way they are. So those are your 2p orbitals, unchanged, unmixed. All right, so let's draw these 4 electrons in their new spots. And there we go. All right, so let's draw this out and compare, so we can compare this with the Lewis structure. Okay, so one more time here. An s orbital is spherical. We're going to add that to 1p orbitals, and it's still going to, I'm going to draw all of these kind of similar. All right, so that's what I'm going to draw as one of these sp orbitals. All right, so I'm going to draw, I'm going to need a couple colors here. I'm going to draw one of these going along that axis. So the central carbon is right there. All right, that central carbon, the one on the left. All right, and then we're going to have another. We're going to have this. All right, so there's one of my one of my sp orbitals, and I'm going to draw another one going the opposite way. So there's my other one. All right, so there's my other one. All right, so those are my 2 sp orbitals, and we're going to overlap them with hydrogens, 1 electron. Oh, let me label that one. That's in the 1s orbital. All right, so I'm going to overlap that one. The 1 electron from the sp, carbon's sp, and 1 electron from the hydrogen's 1s orbital. So those are going to be your 2 shared electrons. Okay, so let's draw, I'm going to do this one more time for the carbon on the right, the central carbon on the right. All right, so I need 2, not write the 2 there. I'm just going to write sp and draw 2 of them, and those are my 2 unchanged p orbitals. And those are my 4 valence electrons for the central carbon on the right. All right, so now I'm going to draw these two sp degenerate orbitals. So there's my central carbon, and so I'm going to do, okay. So that is overlapping with that. That's a sigma bond. All right, so those are my 2 electrons in there. All right, sigma bonds again are bonds along the internuclear axis, so like head on. Right, so I'm going to draw this one now. Okay, there's my other sp orbital, and that sp orbital is going to be shared with the second hydrogen. Right, and hydrogen only has 1 electron in the 1s orbital, so that's going to look like this. Right, so that electron is being shared with that one. Okay, so these are all sigma bonds. They're all head-to-head sharing covalent bonds, so they're all known as sigma bonds. Okay, so we're going to need a couple different colors here. All right, now we need to draw these sharing of this bond here. I'll do this in, I'll do this here. I'm going to share that one with this. I'll do that in green. So these are going to be your p orbitals. So imagine this is like along the x-axis. All right, and the same thing here, x-axis. All right, so those, I can put an electron there or there, but it's all just kind of in that region, right? So I'll do this in green. So they're not head-to-head bonds. So what do we call side-to-side bonds, sharing bonds? All right, they're called pi bonds. All right, so there's your pi bond there, and I'll do another color here. Now for these 2 electrons sharing, I'll use orange. So this is the p orbital along the y-axis, let's say. Okay, and so they're somewhere in there. So they're going to share side to side. So there's going to be a second pi bond, right? And so that's one way to visualize an sp hybrid, or in this case, a triple bond. So anytime you have a triple bond, the one of them is always going to be a sigma bond, and the other 2 are going to be pi bonds. Right? When you have double bonds, the first one's going to be a sigma bond, the second one's going to be a pi bond. All right. Anyway, not to get off track here too much, let's highlight what is important. The key takeaway. Okay, when you need 2 effective pairs, all right, around the central atom, you're going to need sp hybridization. All right, so I hope that helped.